This is an introduction to exercise 7.6 on area under a curve and 7.7 areas between curves. As I mentioned, I'm combining them together. They're very similar, but you must know both skills. It is very important. Something I introduced in the last lesson was signed areas. Essentially positive, negative. Remembering that if a curve goes above the x-axis, it's a positive area under the graph, and if it goes below the x-axis, even though area inherently cannot be negative, your calculation will give you a negative value. Remembering the same principle applies. You cannot have a negative area, you cannot have a negative distance, negative time, etc. So, as integration is based on finding the sum of y values depending on the shape of the graph, it can have a positive or a negative area. When the curve is above the x-axis, as I mentioned, it's positive. If it's below, it's negative. So if we have a negative area, what we need to do, we can do a couple of things, but we essentially need to subtract the negative area, right? That's what we're doing. In order to add the area, we're subtracting the negative area to get that answer. Let's go through an example. It's probably a little bit more difficult than we should start off with, but I really wanted to go with one where you don't have a calculator and it's a graph that you should be able to generally understand the shape of. Example 8 says to find the exact area of the regions enclosed. So the key word that you see a lot is enclosed by, etc. Okay, so that's something you hear a lot in your exams. Enclosed by the graph of y equals to x bracket 2 minus x plus 3. And the x-axis. So the first thing I always see is, do I know the shape of the graph? Do I know key features? Is there anything that I need to know? Well, y equals to x bracket 2 minus x plus 3 expands out to actually I'll write it on the left hand side. I'll leave a little bit of space. Expands to y equals to negative x cubed minus x squared plus 6x. That's just something you can do by hand. Looking at that, I know a couple of things. The first thing I know is that my shape is going to be, because it's a negative cubic, it's going to look something like this. It's not in the point of inflection form, so I know it's going to have a maximum and a minimum, or a minimum and maximum respectively. And I also know its x-intercepts. I know my x-intercepts by looking at this form, of course, where I let y equal to 0. Therefore, when I let y equal to 0, I have x equals to negative 3, we'll go in order, negative 3, 0, and 2. So hopefully this is just revision so far. Before I do any calculations, what I'm going to do is I'm going to graph it. A very rough sketch, as long as I know where the key points are. So when I sketch this with a vertical line, there we go. When I sketch this, I'm going to label my x-intercepts. I've got negative 3, I've got 0, and I've got 2. Doesn't have to be scale, this is just for my understanding. I know that my graph, again, the shape of it is minimum, then maximum, passes through x equals 0 as well. So, it's going to look something like this. Again, the actual shape of the graph, or the actual coordinates, isn't as important. Just while I'm on this note, another gentle reminder, make sure that your graphs are not hairy and don't look like this, yeah, or furry as some examiners say. You will lose marks for that. I did notice at least one student doing that in this act, so just make sure that they're solid straight lines. Okay. Find the exact area of the regions enclosed by the graph. So what I'm asking for essentially is, I don't care about this area out here or here, because it's not enclosed by the graph and the x-axis. So I'm looking for what's in here. There we go. What's in here and what's in here. Agreed? I'm going to give them names. Let's call this one Area 1 and Area 2. The names don't actually matter. That's just for my sake. Okay? You don't have to include this, but I highly recommend you separate it into different parts, especially if you've got a more complex equation. Let's find Area 1. So Area 1 equals 2, and I'm going from 0 to 2. Right? So I'm going to go from 0 to 2, because that's what my domain is. My function, so the area under the function is, and I'm just going to go straight into using the expanded form, just to make my life a little bit easier. Negative x cubed minus x squared plus 6x. You know what I'm going to ask, right? What am I missing?
dx.
Thank you very much, dx. It's a small but stupid thing. Yeah, you don't want to lose marks over that. Good. No plus c when we integrate again. Remember, it's a definite integral, so no need for plus c. When you continue to do that, you end up with negative x power 4 over 4 minus x cubed over 3 plus 3x squared from 0 to 2. If this is going a little bit too quickly, just take your time, do it yourself. And if you're stuck, please make sure you go review exercise 7.4. Doing that ends up with an answer of 16 over 3. A quick reminder, if you have a substitution of 0, so in this case, of course, you'd substitute 2, and then you substitute 0 and subtract it, right? If you're substituting 0, don't always assume that you're not going to have a subtraction. Unfortunately, that does come up quite a bit, where students will say, well, let's say you substitute 2, great, get this answer. You substitute 0, well, there's nothing there, so you just write the original answer. Sometimes, depending what the function is, you can have a constant there as well. Or you can have an answer that has more than 0. So 16 over 3, and then we're going to find area 2. Okay, now, again, key point. Area 2 is below the graph, correct? Below the x-axis, sorry. It's below the x-axis, so there's a couple of ways we can write this. I'm going to show you 3 different ways you can write it. You don't have to know all of them, you just have to use one of them. The first one, which is in my opinion, the easiest one, is to just write negative of from, and we're using the new domain, from negative 3 to 0, and I'm just going to write y here, so I don't have to rewrite it many times. That's the first one. Or, alternatively, just like we learned in the properties of the definite integrals last lesson, instead of writing the negative, we can just switch our domain around. So instead of going from negative 3 to 0, 0 to negative 3, which will give us a negative value. The final option is not in the study design, which means that you don't have to know what this is, you don't have to learn it, you don't have to know how to read it. You just need to know it probably exists, yeah? Which is absolute values. Oops, that should be negative 3. For those of you doing spec, this might seem familiar. But absolute values just means the positive version, okay? But that one is not as important. I highly recommend you just focus on the first one, okay? So let's use the first one, which equals 2, and I'm a negative in the front of, and I'm going to integrate that, which gives us negative x power 4, same thing, over 4, minus x cubed over 3 plus 3x squared from negative 3 to 0. Make sure you don't accidentally do both. You don't add the negative in the front and switch the domain, because if you do that, you'll end up with a negative value again. A quick reminder, you should only ever use the square brackets when you have the domain from negative 3 to 0 written in. So the next step, where you'd normally go, for example, substitute 0, take away substitute negative 3, don't use square brackets again. Use curved brackets, your normal solving ones. Solving that gives you an answer of negative bracket negative 63 over 4, where negative 63 over 4 is that integration, and the negative up the front, of course, gives you a positive answer of 63 over 4. Of course, then we just get the total area. Total equals 2, we add them together, 253 over 12 units squared. Once you've finished writing that down, can I get you to get your calculators out? Thank you. For those of you in the recording, watching the recording, this won't come up. Yes, what's up?
Can you just move it to the side so I can see the... Thank you.
You're very welcome. What I'd like you to do is go to the graphing table and type in our function. So that's going to be x bracket 2 minus x, x plus 3. If you hit enter, you will notice that it might not come up on your calculator. This is something that's happened in the SAC as well. Does anyone know what I need to do, or what I should troubleshoot before complaining about my calculator? So I can go zoom, auto, and nothing comes up. Which means that either function doesn't exist, or there's just some technical issue. What should I troubleshoot first? Let's say this comes up in an exam, or comes up in a SAC. So, perfect, you check you mean if it's been defined, or do you mean the function itself?
If you write it correctly.
Yep, so I double check the function, x bracket 2 minus x, x plus 3. I'm pretty happy with that. It's exactly as it is written here. Now, for me, the first protocol is always just check my definitions. And I'll tell you right now, that's not the answer in this particular case, but that's my first protocol. So I go to main, I go action, command, clear A to Z, and hit enter. Right, done. It'll clear any definitions, any hidden definitions for X I might have. I'll go back to the menu, graph, and graph it again, and it's still not working. This is something that's, I don't know, the class pad's a bit quirky. You need to add a times. X times bracket 2 minus X. Yeah, this happens a lot, unfortunately. But X times bracket 2 minus X times X plus 3, and then your function will appear. Okay? Just so that you are aware that is something that can happen. Great, alright. I'm going to go zoom, quick standard. It includes all my points. Great, I'm happy with that. Okay, I've got my key features inside my window. What I'm going to do now is making sure that the graph is highlighted. I'm going to click Analysis, Graph Solve, or GSolve, and then Integral. There should be 3 options. The integral root, and integral intersection. I'm going to first show you why the first one's not very helpful. So let's click integral dx, and you'll notice that as you press the left, right arrow keys, you end up picking some arbitrary points of x. Yeah, and if you try to get exactly to -3, it gets really frustratingly annoying. So exit that or press escape and go analysis, gsolve, integral root, remembering that root is your x-intercepts. And as you go left to right, it will automatically select your actual intercepts. In this case, if I wanted to only find area 1 or area 2, I can select those specific domains. But let's say I want to find the area of the whole thing. I'm going to hit EXE on the first option. It'll draw a solid line now. I move to the right, and I'm going to go to the 2, 0 coordinate, because that is my other x-intercept. That's the one that's enclosed. So I enter, and it highlights the area that it's going to include. It'll automatically have it as the area and not just the negative, which what I mean by that is saying it's already done that negative area aspect, calculation aspect. So you should end up with an answer of 21.083 recurring, which is what 253 over 12 is anyway. Any questions? Thanks. Alright, are we happy to move on to the next bit of content? Are there any questions about finding the area enclosed by the graph? Please note that another common form of question for this is saying enclosed by this function, the x-axis, and x equals to 3 or something of the sort. Just define your domain as you see fit. Area between curves, let's move on to the next one. We use similar ideas to find the area between curves, except if I give you 2 curves, you then apply a new rule to be able to find the area between those curves. The general principle is very straightforward. I picked some very easy examples for this. There will be some tricky examples in your textbook. Find the area of a region enclosed by the graph of f of x equals to x cubed and g of x equals to x. My first point of call, of course, is always to graph it. So let's graph our function. Let's all pretend that goes through the origin. Thank you. Okay. I've got f, I've got g, and the area enclosed by those 2 functions is only this area here. And if you think about it doesn't matter how far you extend it, the rest of the graph is not going to be enclosed. So that's it. That's the only area we're focusing on. I'm going to label my points. I know, of course, that's 0. This one is going to equal to 1. And this one's going to be -1. Great. Let's find our areas. I'm going to label this one as area 1. And this one as area 2. That is arbitrary. You can name it whatever you want. You can call it Stephen, but that's up to you. Just make sure you write let area equal to Stephen or something of the sort. Actually, you know what? Maybe don't write that on your exam, but that's just something you can theoretically do. Okay, let's start with area 1. So let's start with area 2. It's positive, it's a bit easier. We'll start with that. Area 2 equals 2. We're going from 0 to 1. Now, the only difference between here, if you think about it this way, the area in between of those functions is to say the difference in area between them. Correct? In other words, we can subtract the area of the top function by the area of the bottom function. So, for example, if I find the area of the top function, and let's say in this case from 0 to 1, it is g. Right? So if I find the area of this, I can subtract the area of the bottom function, and I'm left with whatever's only in between. So, using that principle, in this case, the area 2 is equal to the top function, which is g minus f dx. Okay. Which equals, of course, you can use your definite integral, x 4 over 4 from 0 to 1. Which would give you an answer of half minus a quarter, which is equals to, a quarter. Okay. Happy to keep going? Let's move on to our area 2. This is area 1, my apologies. Area 1 goes from -1 to 0. I'm going to subtract. Now I'm thinking to myself, the area enclosed by the graph, in this case, if I find the area of this one here, right, and I subtract the area of this one underneath here, I should be able to end up with my function. Again, there are a couple of ways you can approach this. What I'm going to do is I'm going to say from -1 to 0, f subtracting g dx. Notice that gives you a negative value inherently, but let's just solve it. That gives you from, yeah, that's correct. Gives you from -1, I should write the actual function in, x power 4 over 4 minus x squared over 2, which gives you from -1 to 0. Gives you an answer of 0 minus, don't forget the initial 0 as well, a quarter minus a half, which inherently gives you negative a quarter, so a quarter. Adding that together, our total area equals to a quarter plus a quarter, so in other words, half units squared. Once you finish writing that down, again, go back to your graph and table and sketch both functions out for me. So x squared, x cubed, and x as well. Don't forget, if you get something very zoomed out, you might want to zoom in a little bit. I like to just use the box option, and then just go zoom square. All it does, it just makes your values of x and y increase by the same amount every time. Okay, once you've done that, you're still going to go analysis, G-solve, integral, and you notice that another option has appeared on your calculator. You're going to click the integral intersection option. And again, you'll notice that your function, or the lines that appear for the domain of your integral function, will only exist at the intersections. Okay, so let's say I want to find the total area enclosed by those two graphs. I select the left one, I move to the right and hit enter again. It'll select the area within, double check that that area is what you want. Then, well, it tells you the answer. Bottom right, the area is 0.5. Done. That's it, which obviously is what we got. Any questions? Okay.